So this was my personal and bone stock Prusa MK3. Now it is a monster. And if you really hate yourself, you can recreate all of this. Let me walk you through. There are 2 filaments and 1 cup. There are 2 filaments and 1 hot end. It can do directional material deposition, a sustained flow of north of 100 cubic millimeters a second, and all of that in a very light package. This video isn't a highlight reel. It is fully chronological, uncut, unfiltered, and some of the times painful. You will witness fails, slightly more educated fails, jaw-dropping encounters, fails, idiot, moments of this is where a problem lies. So this is where a problem lies. And then ultimately great success. So if you're looking for clean results and fast conclusions, this is the wrong neighborhood. But if you're into watching an engineer go mental, melting plastics at unreasonable speeds, and slowly converging this machine into something that actually works, my name is Jan, and I build stuff so you don't have to. So welcome to this 90 minutes deep nerd dive. This was an innocent Prusa MK3 forcefully dragged into the high-speed era of 3D printers. And also, I don't want to brag about it, but I was being awarded with a Partner of the Year by our sponsor PCBWay. More on that later. So I'm pretty sure I'm the only one who got that. Let's start with the intro.
Da 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 da.
So this is the current state of my MK3. I did some test setup here to verify that everything fits and moves. We're gonna get rid of the mock-up parts, put on the real parts, which are scattered here around the bench. And in the process, I'm gonna measure all of them to see what the actual weights are. This is the 2X version of the hot end in question, including the nozzle, 2 copper heat breaks, and the push style fittings on top of here. This whole setup is gonna weigh in at, spot on 69 grams. We're also gonna need some fasteners, which are 14 grams on top. These actually do weigh quite a lot. And then of course we're gonna need some additional hardware. There's gonna be a 30 by 30 fan, then there's gonna be a cooling duct, the 2-sided carriage mount, and some cable guides. So all of this hardware comes down to 180 grams, which I'm kind of pleased with in terms of how much flow this setup will generate. So let's put all you see here back on the machine and try to get it running. And then after everything is set up and working, we're gonna rip this machine to its maximum capacity. We'll find out where that is. But before we do so, as you can see here, there's stuff on the build plate, and after a first and successful print, a bench doesn't look anything like this, so we gotta do a deep dive into what's our problem here. So if you got no idea what we're talking about here, this is my take on a very potent hot end that does a lot of cool things. So first off, it's open source, so you can pretty much download the files, order some parts on the shelf, and build a printer with it that can do around 200 cubic millimeters per second. This is the 4X version, and this has been on like the Creality CR10 Max as seen in the last video. Unfortunately, it looks just like I've left it a few weeks ago. So the hot end I've installed on the Prusa is the 2X version of it, so 2 filament inputs. When I did the first test print yesterday, I ran into an issue with heat creep. So I didn't have any problems on the Creality with this. I never actually had problems with this here on the Minuteman machine, but now I do have, and I have to investigate. So every hot end basically consists of 3 main areas, which is the hot end, the heat break, and the cold end. And if we disassemble this, The Heatbreak's main function is to separate both of these zones. So there is a very thin walled tube, either made out of stainless steel or titanium, coupled with a copper block on one side. So what ended up happening on my first prints yesterday was that when I put in PLA, after some point in the print, this eventually got too warm and the filament melted somewhere up here, which it shouldn't do. It should be in a solid state right up to this point where it enters the hot end. And as I said, I've never run into these issues before and I just made very minor changes. So we have to investigate what this is all about. So this is where a problem lies. There is already molten plastic here sticking all the way in the Heatbreak. My first thought was to apply some thermal paste to get a better heat conduction between these both parts. The only thing that it is helping is if you want your hands covered in stuff. So somehow it is getting worse. I couldn't get the heat breaks unstuck, so I unscrewed them and will be replacing them with fresh units. So this is the one that has been on this machine for an entirety of at least 15 printing hours, probably more. And these are, I mean, not identical, of course, but pretty much the same in terms of how these holes are, toleranced, etc. So the only difference is that here I had the space to do 3 M3 screws to do the actual flexure part that clamps these two aluminum halves together and secures the heat break. So I don't know. I'm gonna equip this with a new set of heat breaks and yeah, start from there. These are the 2 new units. And I'm gonna actually try to seal them up with this stuff. This is like exhaust putty. So we're gonna throw a dab on here. Yeah, while this hardens, I'm gonna clean this place. It's a mess. Everything is back together, as you've seen with a new set of heat breaks. I have this settled in at 250 degrees for at least 10 minutes. And as you can see here, cold end temps are at 16 degrees something, so not that much heat that is traveling up there, but the thermistor, which is sitting here, is not at the heat break itself, so there may be some deviation. I'm gonna load in some PETG, and before we do that, I'm gonna sweep across this whole thing with the thermal camera. Okay, this is the complete view, pretty decent temperature readings across everything here. It measures 275 where the heat cartridge comes in, and then somewhere like 130 on the outside, but pretty evenly. And then if we're having a real close look, it's 125 up here and like sub 50 in the heat break tubing, and then cold end outside temperature 35 something. Alright, so I finally got it to extrude some material at least. And I think now I do have all the leftover PLA flushed out of the system. I intentionally unscrewed the nozzle to see if any debris I created during my whatsoever has contaminated any of the melt channels. I'm gonna extrude some more material, then pop in the nozzle again and see if we can get some material out of there. Okay, extruding small amounts. Okay, there seems to be something weird. I can't wrap my head around this for now. But if you have a look at the extruded material, even though I got low with the temperature, this is 230 or 225 at the end for PETG. And it's coming out really bubbly. I'm gonna put it in the dehumidifier overnight, have a look at the cat and see how I operate from here. Something smells off. So it's the next day, it's Sunday actually. I maybe got 2 hours to do some additional work here on the machine. Because if you bought the parts for the 4X filament hot end in the last video and are in the process of setting this up on your machine, you may encounter some same problems as I do. So I actually think the temperatures up here are fine. I don't think there is enough temperature, so PLA material should be molten here in the heat break. But what I think happens is that filament, if not both channels are being driven at the same time and the same speed, you may not push the filament out of the nozzle and instead up the other channel. And then, of course, once the material fills up the heat break, it will solidify there and don't get any further. And because the 4X hot end, I was very aware that this might happen, but it never did, so it just worked flawless. So I identified three main things I have changed from the last setup. This is the generation I've been running on the Creality last time. As you can see here, there is an M6 thread for the push style fitting, and beneath that there is some room to accept a PTFE Bowden tube, just to line this, reduce friction and all that stuff. And in the latest version, I wanted to get rid of that because it was finicky to get this in here. I came up with this design that adds a little bit of a funnel here to guide the filament in there. And yeah, then it's just raw aluminum and it comes down here to the heat break section. If you ask me, I don't think this plays the major role here, but it might be a few of the last percent. Second thing I changed. Before we were doing all our experience with big nozzles, somewhere in the range of 0.8 to 1 millimeter. And now I do have the 0.4 because this Prusa is able to run very fast. The Creality was not a very fast machine, therefore I could just max the hot end out if I had a big nozzle on there. This Prusa is, and we're getting to that in a minute, so I opted to go with a smaller nozzle. This smaller nozzle will create a lot more back pressure here. So once one filament is being fed in, the chance of actually pushing up on the other side is a lot bigger. Which leads us to change number 3. And this is the extruder setup. So all tests conducted before were either on the Minuteman machine, which features 4 independent extruders, but these are all like hooked up parallel to one of these drivers here. So they're pretty much controlled as a group. Then here on the Creality, I was using this Bondtech one-off with connected shafts to all of these pusher assemblies. And therefore, with this being connected all the way, if there is a step loss or something, it is affecting all of the channels that are being fed filament into. So now here on the Prusa, we got 2 totally independent working extruders. I think at the very first beginning when I put PLA in, it was actually extruding pretty fine, up to like 90 cubic millimeters or something. And then I noticed, oh, they're skipping. And I turned it off, and basically my whole process of basically pushing the molten filament from one side to the other began. I pretty much woke up this night and thought, hey, maybe you set 2 different currents to these motors. And indeed, this one was at 1 amp, this at 0.75, because these are not connected to the same mainboard. They're also not getting the same voltage. This one is 60 and this 24 volts. My basic theory is that with this setup now, since we have this all open loop, it may occur that just one stepper is skipping steps for whatever reason. And then filament is being pushed up outside, and then basically everything is clogged from then on. So we're gonna be super careful not to skip these. And I think I left this yesterday evening with a working PETG setup. So I'm just gonna wing it and try to do a first print and see if this system holds up. And if it does, we're gonna switch back to PLA to confirm our theory. And if we get into another clogging situation again, I do have another plan to figure it out. So let's do that. Yeah, well, I thought I had left it in a working condition, and I surely did. But yeah, I was feeding in filaments both simultaneously at the same height. And as it turns out, the right channel is blocked big time. I could unclog the left one. Okay, time for plan, I don't know, E or something. And well, plan E consists of an M6 grub screw So basically I want to try just blocking one of these entrances off, running only one extruder and just feeding in here. So if material gets pushed up the other side, it just be blocked. There will be a big puddle of molten material inside, but the only way out is this way. And I'm gonna put in PLA because it has the lowest glass transition temperature of the materials. And if it works with that, I know that my heat break temperatures are fine, and the problem is due to two filaments being fed in at the same time. One side closed up. Fiberlogy, high-speed PLA in the single left lane. Let's see how it goes. Okay, I'm starting to just push feed it by hand. Okay, so no problems here. It is a bit flimsy right now because it's missing, of course, one of its two mounting points. But should we do printing? Real test application? So you should have been able to see the first half of the print, but I forgot to hit record. So yeah, this is working pretty fine. I forgot to upgrade the printing profile properly, so it's at 1mm nozzle flow rate, but this is just 215 degrees. And it's handling these 50 cubic millimeters just fine. It's rather early to draw the conclusion, but heat break temperatures do seem to work for PLA. Everything else would have surprised me big time because there has been so many prototypes before that have just worked. So there you have it. First print finished without cooling. This whole blob in just 8 minutes. It's not looking too shabby, but you can see how warm it still is. There's been a lot of flow coming out of here. So this has been 50 cubes all the way. Make a prediction if running 2 channels will just double it, and I have no idea where the limit is. This was pretty effortless. We didn't have any skipped steps or something. And this is just 215 degrees, so I have no idea where the real limits are. But make a prediction now. Okay, I don't have much time left, but all I can do for now, I updated the printer profile, so 0.4 it is. I sliced it again with a lot less layer height, but still 50 cubes of flow. And we're gonna hook this makeshift CPAP to it. You'll see in a minute what is being coupled to that to run it with a bit of cooling. By the way, chances are high that I'm gonna rip this nozzle off because it's moving too fast. But to be honest, I don't care too much. I gotta rebuild it anyway. Okay, we would have needed a longer purge line, but I'm just gonna let it run. The reason for this is because the right channel has been oozing out during the waiting time, and now it's got to be slowly filled up again before we hit full pressure. That's, I think, what you can see here. This is a bit less dense than where we're at right now. So let me crank the speed up. Oh, it did by itself. But this is just 50%. Let's add a bit of cooling. So this is 50% and my bench is already starting to shake violently. This one is pretty much unsupported here. The other of the benches I upgraded with some kind of support down there. Maybe I should add that to this bench as well. So it didn't finish, but there was an error from one of the TMC drivers. I have to look into that, but this is another story. So again, has been working really good. No problems here. Nothing is tuned, no parameters for retractions, etc. are done. Nothing is... This is literally the second print it does, and I think for that it's looking pretty damn fine. So I think this calls for another night of thinking about what is happening here. Next time I'm on the machine, I will get the second one installed again and see if we can make them run at the same time. There's still some work to do. So, next day, next experiment. I'm feeling a little bit lucky. So I reassembled this with 2 heat breaks. Both extruders are hooked up. I double checked them completely, looked at the alignment, looked at the currents. So they run as parallel as possible. And I also have like the filament put to the exact same length. And I'm just gonna insert the filament with the extruders, not by hand or stuff like that, so they should be touching the melt zone pretty close to each other. If our theory is right, that heat break temperatures are okay and it's just a matter of these guys pushing at individual feed rates, we're gonna find out now. While we were talking yesterday about things that have changed, I put in the 1mm nozzle again. So we're gonna check if the system works with a bigger nozzle, so less force upwards into the channels. If this works, we're gonna switch back to the 0.4. If it crashes then, we pretty much pinpointed our problem to a very small degree. Also, this enables me to do a flow test on a bigger nozzle, so let's do that first, see if we can get any results out of there. Hopefully this works, and if it does, let's switch to a smaller nozzle like we were doing in the first place. Okay, while this test is running, I'm gonna show you a bit on how I do run these filament tests here. Because what I wanna have is like a graph for different flow rates and temperatures, so we can make a temperature variable through the print and don't overheat material where we don't need it, and vice versa. So what I'm gonna do, I am running the max flow test and I set it up from 35 all the way to 125 just as a ballpark guess. And I'm gonna start with the temperature at 205, so very low for PLA. And I'm just gonna let this run until it barely starts skipping. And then I'm gonna write that number down and raise the temperature by 10 degrees and let it run until it skips again. I have to be very careful in this kind of setup. I don't wanna like mess it up right away. So as soon as I do hear the first click, I'm gonna set like the speed down to 50% and see if it catches again. And then we make like notes for 205, 215, 225, etc. And then we can make a nice little graph out of it and put it into a post-process G-code editor. We can link temperature and flow rate to our hot end. Still going, 205 degrees, almost at 60 cubic millimeters a second. Don't want to jinx it, but this does look pretty good. So this is becoming almost a bit scary. We're running 70 cubic millimeters at 205 degrees still, but you can see that our PWM signal to maintain that temperature is already, like on average, at least above 50-60% or something. But this is still going. So we just surpassed 85 cubic millimeters and extruder started skipping. I raised it to 215 and now it keeps going again. Okay, so we've cracked the 100 and I'm up there at 235. Going without skipping steps, but we can see that the PWM signal is pretty much maxed out for these heaters. Probably have a bit left, but not too much. This is 105 cubic millimeters. So this is running almost 120 cubes, and as you can see here, I'm maxed out. It doesn't reach the set temperature I have in here. So I think we're pretty much done here. 125 should be the last. This is 123. It did finish. Okay, I take this as a huge W for the Hotend itself. Maybe not for the usage of small nozzles, but we'll get there. So this is the result. Of course, you can see me fooling around with the temperatures in here. Let's fix that and rerun the test with variable temperatures. So we're gonna do actually pretty much the same thing as before. This is again a max flow test, starting from 50 all the way here to 100 cubic millimeters. And I have this script in here, which is the SB53 by Salim. And yeah, this does an analysis of the flow rate throughout the print. So it is going 15 minutes. And right here you can see this is like the skirt it is doing, and then the requested flow is rising linearly. So what we can do now is take these values I collected throughout the first flow test and plug at least 3 of these values in. Maybe the 205, the 225, and then 240 or something, which it was able to reach. So this is what I plugged in. We want to have a base temperature that is not too low, that it's gonna stick to itself, etc. Then we have our middle point, which is 215 degrees at 85 cubic millimeters. And if we're gonna go full blast, I set it to 240 at 115. And now if I hit refresh here, it's gonna do me a plot of the requested temperature. And you can see here, right at the end, it starts with a different slope than it did before, which is kind of expected. This is what my numbers are getting. For the last few percent of performance, you need the most power added. And then we're gonna hit generate and save file. And now we have uploaded this with variable temperature, which we're gonna run now. So we're almost at the end here of this second extrusion test. As you can see, the layers are looking pretty close to each other, so our main variable here becomes viscosity, and this is what we're dialing in with the rising and variable temperature. You can see here there is a slope to it, it is running up, and we get a variable target temperature here that is being determined by the G-code, which is applied by the script. And we're already at 80 cubes again, and this will finish at 100. And we're pretty much on the last layer here. As you can see, it does lift here up the build plate, but here where it doesn't, you can see how good the layers are stacking on top of each other, and we have a very even viscosity. Right now, pretty much 100 cubes and 227 degrees. Awesome, this works. All right, with that print out of the way, let's finally focus on the printer we're doing all these experiments on. So this is my personal Prusa MK3, and I bought it in 2018, I think. I do even have some footage of Thomas and me building this machine on the granite plate, which is basically just below there. And since then, this machine has been an absolute trooper. For the last couple of years, I had it set up as a TPU-only machine. And this machine has been running like a champ over years. You will see the print time count on this actual machine in a minute. Until a few weeks ago, I have never done any maintenance whatsoever to this machine and it just ran fine. This has changed. So this machine is pretty much as upgraded as a Prusa MK3 can be. And there's someone that played a major role in this, and this is Julien. So Julien is a long-term buddy of mine, which has helped in a lot of projects here at the company. Either it was the solar robot or any other like Minuteman related stuff. Basically, he helped me set up the firmware on the first day to make it all happen, etc. So Julien has upgraded this printer with a lot of cool mods, and he has made a video about that. So since you're ball deep into a video that is probably an hour long or something, I guess you can spend additional 15 minutes. And this would be the greatest point in this video, I think, to switch over there. Have a look what all has changed in terms of electronics and programming and how to set this up. And I think this is a pretty good guide if you want to recreate something like that. So again, Julien, thank you so much for helping me out on this project. The link to his video will be in the video box somewhere down below. And let's see what I did on top of that conversion. Alright, so let's cover a few things and start with the motors on X and Y. I think this is also something Julien has explained, but I have these motors sitting here for almost a year by my boy Omranello from Dubai. And he sent me those in order to get the Minute machine going. And I did have a solid plan for those, but yeah, I never pulled the trigger on it because there was so much other stuff to do. But now I think on the X and Y axis they have found a perfect spot here, and we can see how much we can crank those up to make this a very, very fast printer. Again, in the switching cabinet you may have seen TMC 5160 all the way for all the motors. There has been this secondary power supply added, which is 60 volts to the motor rail. For this particular setup, I added this additional SKR board as a daughter board to the existing Manta. For this particular setup, I needed another driver. It was not possible to do that on here. Another fun fact, in case you didn't watch the video by now, this here is the total print time of the Prusa. So it's just shy of 420 days of actual printing time. I got proof of that. I filmed a short clip when I disassembled the Prusa. And Julien did go all the way to recompile Clipper to put this as an origin value in here. So we got another like 20 hours to go to celebrate that milestone. Well, yeah, and then let's come to the core things I added here, which is of course the 2X version of that Hotend. I think all the files of this Prusa, including the extruder setup, the mounting, the whatever, will be available on the GitHub. You have to decide for yourself if you're up for the tinkering. You have seen how long it took me to get this somewhat working, and we still have to go back to a smaller nozzle to confirm that it is working on there as well, or maybe ditch smaller nozzles altogether. So this is still in beta status, and you should know what you're getting into if you want to rebuild stuff like this. But then again, try to find a Hotend that does easily 100 cubic millimeters per second and is still not maxed out. So what we got here is a complete replacement for the X-axis carriage. This duct is working as a structural part, so basically there are 4 screws in the back and then everything falls apart here. There are dedicated parts for cable routing and mounting points. There is the original Prusa Pinda probe. There's one slight issue I have to get around. It is hitting the connector here to the bed. So basically right now this section here has to be excluded from my printing profile. There is no loss in travel in XYZ. It does everything the original Prusa does. It does home here with sensorless homing on X and Y. And now this is where it gets really interesting. Usually all my type of testing was done with a single extruder that has connected gears. But so many people mentioned in the last episode that I should do variable ratios. I did prepare, or let's say Julian and I prepared a lot to do that. We got a routine set up that does a fixed ratio by G-code commands. And we're gonna see if we like crash the Heatbreak situation again with that or if it runs through. The whole setup here consists of just, this is Amazon's finest MK8 extruders, like 15 bucks a piece. And then I coupled it with what I had on hand. These are LDO speedy powers. And all of that has been connected to a Mac base. And that is, I have been fooling around with ideas on how to or where to actually set this up. And I couldn't make my mind up about it because I was experiencing a lot of issues with long and too tight bent PTFE tubes on the previous versions. So I opted to go with something I can pretty much move in space. And this has been a very smart decision for now. And yeah, then I took some inspiration from Nathan's Stonewolf printer and added a few clips here to the PTFE and CPAP tube. And yeah, well, talking about the elephant in the room, there is a CPAP connection, which is going conveniently to this Makita leaf blower. And this has been created pretty much last minute because the CPAP radial fan I bought never showed up to my door. So this is pretty much what I came up with the day before we were starting our tests here, and I gotta say I'm pretty impressed. I wouldn't go with the 18-volt version, but I'm sure there is really dirt cheap leaf blowers with 230 or 110 volts available, and this makes up for quite some steam on here. We're gonna max this out in a minute, I guess. But yeah, this is pretty much the setup. And yeah, maybe very lastly, this is again high-speed PLA from Fiberlogy from Poland. And this stuff has been my reference in terms of flow rate. It was doing 120 something when the heaters were maxed out. I think this is spectacular for a PLA. So I did screw in a 0.6 millimeter nozzle. Basically same test, but this time from 30 to 100 cubic millimeters. Let's see if we can reach 100 with a 0.6. Rest is pretty much the same, so let's just go. Okay, same test with the 0.6 millimeter nozzle. As you can see, there is not too much of a difference here. So 205 with a 1 millimeter is around 80, and 205 at the 0.6 yields around 70, and then 93 compared to 85. And I don't know if it did skip at the end, but I'm pretty sure it did ran through without doing any major under extrusion. We can check that. So print is estimated at 33.65. Yeah, probably a few percent. I'm not off by a order of magnitude or something. I have the wrong numbers dialed in. This was extruded at 100 cubic millimeters a second with a 0.6 millimeter nozzle first try. We're getting closer to where we want to be. So alright, let's put on the 0.4 millimeter again. I want to see how this performs, if it does work. In case you're wondering where the silicone sock is coming from, I went ahead and sketched up this mold for it. So basically you're gonna put this like this on the printer, a little bit of support here on this ring, and then you're gonna fill this cavity, let's say a little bit down the brim, with high temperature silicone. I used a 2K variant, but I'm pretty sure it will also work with 1K silicone. It will work without a vacuum chamber if you don't mind very small bubbles here. And then obviously you fill it, push this guy in, maybe add a clamp on top. See that it squirts out material out of all of these guys, and then after curing time you can unmold it, and it will fit not only the 2X but also the 4X version. So this one should be getting pretty rowdy towards the end. This is 500 millimeters per second printing speed at 100 cubic millimeters per second. So let me switch on cooling and see how far we can go. It did not only finish, it does look pretty good actually. There's no like pressure advance and stuff set up, anything. And I do keep running into problems that these are lifting at these speeds and cooling. But again, there are no signs of under extrusion here. This is at 100 cubic millimeter max flow, but since I do only like typed in 10k of accelerations, we're not gonna hit that permanently. Like the mean of it will be somewhere, I think, less than 70 cubic millimeters, but still we were just at 205 degrees on a 0.4 nozzle. Whatever happened on day 1 that followed me until day 4, I think it's gone, whatever it is. And I'm kind of relieved, because if this were to be of a serious problem, then everyone that has already like built the 4X version would be in the same trouble, which gets me into trouble, I guess. I think I have proven that this setup will work. Now it is time to run input shaping, essentially get all the parameters there, and then, I don't know, print a fast Benchy or something. I don't know. We'll not get into 100% dialed in territory here. This takes weeks and hundreds of prints, etc. So don't expect this to be running near Minuteman limits or something. But it would be nice to at least see where the limits of the motors are, and if we can like do a print with a 0.4 millimeter nozzle that utilizes all the flow that this Hotend can do, that would be pretty dope. So let me see how we can reach that tomorrow. Alright, so again, another day, I guess this will be an all-nighter. But have a look who joined me on my late night quest. It's Julien again.
Hi guys.
So Julien, what are our plans for this evening?
So first we're going to do some input shaping and pressure advance tests, and hopefully we are printing out a pretty fast Benchy.
Alright, that does look like a plan where nothing could go wrong. So let's do that. So the first pressure advance test has run through. You may have seen that in the footage, just the left extruder is getting the pressure advance values actually updated and the right one is just going as is. So we'll have to figure out a way where it will apply to both. Yet again, we ran into a issue that is not easily solvable. So that is a problem for future Jan, I guess. So to wrap this up, we just want to see something, a real world print. So we're gonna throw a Voron Testcube on there and just watch it do its thing. So there you have it. Printing speed were just around 250-300 millimeters a second with 5K accelerations. But there is nothing like pressure advance or something set up. Especially if we want to max out this hot end with a small nozzle on there, we need to go way faster. But we're working on that.
Are you satisfied?
I am.
And you still haven't watched the build video? Over here.
Alright, so I'm not 100% sure where we left off, but I know where we're gonna go back into it. So let's hop on over to my screen and discuss some things. Starting with the results of the input shaping. What you see here is the last test we did on the y-axis, so the bed moving. And as you can see, this looks somewhat clean. We got a peak here in the 55 Hertz region. You're gonna have a look at the green line. The purple line is all of the axes combined. There is a recombinant shaper of the MZV. We're just gonna poke that in here for now. There is surely a lot of different stuff we could figure out there, but for now we're gonna roll with this one. On the x-axis, however, this does look a bit different. This is x, so basically the hot end moving on the rail. And as you can see, this is a bit more messy. So a red line is what you're gonna have a look at. And we got a response somewhere at the 97 Hertz region. And something, there is some gibberish going on here and something at 190 Hertz. And basically, I don't know if I have a clip of this, but this is mostly what the belt has been doing. So I think I gotta find a solution to tighten this even a bit more. If you have a look at the rest of this, the other axes combined, I'll put a video here. Basically, the whole machine is moving like crazy. So the whole like upward frame isn't as stiff as I would like to have it. And of course, this machine has never been designed to run those speeds. So this machine is kind of exciting my whole workplace here. Before we do any 100% dialed in input shaper settings, we're gonna get rid of all of that, obviously. And I wanna have the hot end figured out, and this is way more important right now. So let's have a look at that. So what you're looking at is basically the very first version of the 2X hot end I had on the machine, but I think there's no video of that. What you can see here, this is basically a derivative of the 4X hot end, and I never had any issues with that. But now you can see a clear cut section of how I designed this. So the heat breaks do bump up to this 2mm in diameter hole here, and then I had a PTFE tubing in here that pretty much bumps up to the push style fitting you put on top of there. And while this was working really clean, I didn't like the way of having to cut that to a very specific length, and then once you had it installed, it was kind of difficult to get out again. So in comparison to that, the right one is actually the version I have on the machine right now. I kind of get rid of all of that PTFE up here, and I wanted to have somewhat of a nice transfer of material from the push style fitting into this Coldend section. It was just running on rough aluminum and then basically goes down here into the heat break. And I got several problems with that. So first off, if you want to load some material in from above here, the fitting is basically 1.5mm short of this diameter here. So what ends up happening, all of the filaments have a slight curve to it. It's never perfectly straight because it comes from a spool, and you end up having troubles to get that in there. I usually had to cut the end of the filament to be somewhat roundish, and then it would go in there. But this is not how I imagine the finished product to be. When I take out the filament from the Coldend and it has been sitting inside the heat break, it kind of gets stuck after a while. So temperatures seem to be kind of somewhere in the range where PLA starts melting, and probably these two diameters don't line up too good. So if you have that here somewhat close to melting and this diameter seems to be pretty much spot on 2mm, and probably this is 1.9 or something coming straight from the SLM machine, then this 2mm filament won't pass back through this section here. So this is no bueno. And then the last really big issue I have, the heat breaks are borrowed from Creality. This is the Ender 3 S1 style, and basically on the 4X version it did work really good. I never had any problems with that. It surely comes down to how much pressure we're gonna put in the whole system of the Hotend. And since I could run the 4X extruder just with very low currents, there hasn't been a problem with leakage. If we zoom in, there is basically this small lip here, and once you tighten the heat break, it basically forms a seal with it by compressing the copper and aluminum together. But with this kind of approach, we're somewhat limited on the torque we can actually apply to here, because we're grabbing this heat break with some sort of pliers, etc. Since the upper part, made from copper, is only press fitted onto the lower part, there is a limited amount of torque we can apply to the system. We gotta get rid of that, but I didn't have any options here. But then I talked with Vase over at Vase 3D, and he suggested using this guy here. This is actually the heat break of the Chimera Hotend. And this basically has this little flange where you can go with a 5mm key and apply torque to the stainless steel section of the part. So we don't end up in the situation that we have to rely on the press fit between those two. We can grab it by the thread. And this is what we're trying to build now. I'm gonna be doing a short montage over getting this heat break installed into this new system, and I sketched up some things on how we're gonna achieve that. We're gonna use the extended length of the Chimera heat break. We're now able to use the 5mm flange to actually secure it. Let's see how good I'm gonna be able to screw that in here. You might have to take a 0.5mm off of there. And then this heat break's gonna sit right until here. And the heat break itself does have a 4mm opening for a PTFE tube. And this is what we're gonna insert here on top. And this is gonna do two things. So first off, we now do have a continuous closed diameter starting from top to bottom. So we're gonna get rid of this up here. Basically, we can take the PTFE tubing, go in there with a countersink and have this fitting bumped up against the PTFE, so getting rid of that small gap here. And also, since this is sitting inside of the heat break, we're gonna get a very good transition here. Since the heat break is a bit longer, we might get heat dissipation to the Coldend. And where we need it the most, on this flange style here, we get a double contact, so more surface area right where we need it the most. Since this is not 100% leak free, there is some material building up here, and this is giving this diameter section a bad time dissipating the heat from it. So basically the lowest part of the heat break, which should be cold already, is being surrounded by plastic, which has a whole different set of parameters in terms of getting rid of heat. And the material coming in from above was melting to a point which we didn't want to have. So let's hope by giving some more torque on it, it will be leak free. And then we have the continuous path coming from all the way to the top to the bottom. We're gonna get rid of the handling problems I have with this current iteration. So I got this guy, which is basically a leftover from the last attempts I was doing, and I never really machined it all the way to the end. So we're gonna stick it. I don't know if I'm gonna be firing up the mill or the drill press. We're gonna make sure that these two cope with each other, get the PTFE in here and all of that stuff. So I'm basically gonna take you on a tour what it does mean if you buy unmachined version. So we're gonna have to cut all the threads by ourselves and make sure that PTFE tubes and heat breaks, etc. do fit properly. So we're gonna do that together, put it back on the machine, and then I got something else figured out. So let's see there. So the whole problem with pressure advance comes down to let's call it a bug in the Clipper firmware. So apparently you can set 2 active extruders at any given moment. And you can also set different or the same values for pressure advance on these both extruders. Since they are synced to each other, and basically the PA is added after they have been synced, only the first of the two has been acting with active pressure advance and the other was just not. So for the whole mixing endeavor, I have to find a way first to make this proper. I have a routine set up to do that, but it would not be properly because we don't have active pressure advance on both of these and we would get weird results. So I tried to figure that out for a future episode of this. For now, what I want to do is print something that is taking the extruder or hot end setup to its limits. So the whole machine was built to be fast enough to throw this around with a medium-sized heat bed, so we don't run into severe cooling issues as on the Minuteman machine because the bed's only this big. But now we can go ahead and have this run at decent speeds, max out the flow of the hot end. So I'm gonna put in a 0.6 millimeter nozzle. This gives me a fighting chance of reaching somewhat above 120 cubic millimeters of flow. Then we're gonna max out the mechanics of the Prusa and see if we can print something as big as the build volume. When I started all of this, again, I thought this would become a short video, but then things started escalating. And since I want to give you the opportunity to build this yourself, I think it is somewhat mandatory to give you all the problem-solving techniques here. And I hope that my last changes now will be working. And if they do, I'm gonna publish these files with this kind of setup here and explain how you acquire the heat breaks, etc. So let's do all of that, install it on the machine and hope for the best. So welcome to my tiny vise here. And we're going to start out with doing the M3 taps. So using a drill for this is somewhat sketchy, but most of the times I think I know what I'm doing. So clutch at a very low pressure and use a drill that is very low on power and has not the biggest weight, so inertia. If you want to go the proper way, use a tapping wrench and some cutting fluid. I'm not going to be doing that. Next up, an M4 thread to do the clamping screw. Followed by a 2 millimeter drill to enlarge the thermistor hole. On top, we gotta retap the M6 threads to accept the push style fitting. I'm actually using 2 taps. So the first is a regular one and the second is an cut off and to tap all the way to the bottom. So we're gonna start with this one first. This ensures that we're in line with the bore, and then we're going to follow up with this one. So just in case all of this seems intimidating to you, you can either choose to have the unmachined version or the one where the SLM manufacturer, and in this case PCBWay, has done all of that for you. It's a matter of price point, I guess. So this would be the perfect opportunity to talk about our today's video sponsor, right? So PCBWay is an online manufacturer where you can upload pretty much any files you desire to be manufactured. They do offer all sorts of stuff, ranging from 3D printing in all sorts of flavors and processes, starting from FDM over SLS, SLM, you pretty much name it. On top of that, they do very crisp machining in up to 5 axes, sheet metal design, and of course they manufacture PCBs. The quality of those parts has been shown on my channel again and again. It has been running on the Minuteman machine for ages, and they do support me with loads and loads of premium items on there. So I can highly recommend chasing the link somewhere down in the video description. Following that, you get a small discount on your first order, and after uploading parts you will receive instant pricing on those, and if there are any problems with that, for example with wall thicknesses, etc., an engineer will contact you and you will find a solution together. Thank you PCBWay for sponsoring that kind of content. Let's go back and drill some more holes. So I fired up the most reasonable mill here in this place, put this in the vise, and already picked up some work coordinates. And now we're going to use a 4.5mm end mill to cut all the features for the heat breaks. So if you could see my face, you would see a real confusion on why this is such a sloppy fit. The reason is I'm an idiot. It's a freaking typo. I typed in 6.2 here and then fat fingered a 6.5 here. So luckily I do have the one that has been on the printer. I'm gonna use this one, make sure I don't screw this one up as well. So in German we do have a saying of "Wat er niet im Kopf has, has in de been." This is a perfect example for this. Alright, so at least I was able to salvage this guy, so we can move on. I will show you this on the machine once it's installed. But yeah, since we're down here, I think it would be a good time to announce something. So in March this year there was a Discord meets here in the company. I have no idea if this is happening again in 2026, but if you want to be part of it, there's a link to my Discord down below. That's the only way you're going to find out, as well as Patreon maybe. And what we did here was like an entire shop tour, running all the machines, etc. And we had a camera rolling. So there is unedited footage of all of that happening. And if you guys want to see like this whole company here, I gotta be posting that once this channel reaches 50,000 subscribers. So if you haven't already, consider clicking that button down there. And also, if you're eager to see that shop tour video, send this to some of your friends. So with that, let's hop on upstairs again. So it is back together. Just for once, I'm gonna spare you some details here. Let's just have a look at how it is supposed to look, and I'm really happy with that. I, as you can see, did some additional sandblasting on the original Hotend to make it look good again, and also that way we can see if there is any additional leak now. As I said, 0.6mm installed, and finally we're gonna run some pressure advance tests to find out some values, then hopefully print something till the end. So now was the time to load into colors of filament to do another thing this Hotend is designed to do. And this is what I explained in the previous video, directional material deposition. So in accordance to the printer's movement direction, you will see different colors or materials. Going on with the good news, I successfully printed 2 pressure advance towers. This was the very first. This is 0 to 0.5. And I measured this to be the best at 0.2, and then I ran 0.1 all the way to 0.3, and now I can measure that and plug in this value for now. Coming to the bad news, there are still a lot of things to do. I mean, very early in the process of dialing stuff in, but as you can see here, input shaping is not really on par. This has been at 20k accelerations throughout the whole print. The y-axis will be our limiting factor here. It skipped steps a few times when I ramped it up to 25 something k accelerations. Okay, moving on. The thing I was trying to get rid of is leakage. And as you can see here, we're still not golden. There are a few things to consider, however. So if I would have guessed which one will be leaking, I was saying the left one. I got 700 square meters of company here, but I didn't have any 5mm key in here, so I opted to build one, and it was rather hard to reach in there, so I would have needed a few things actually to make this a more and proper seal, but I want to have some fun right now. Slice something which is big and fast and lay down some material. Let's do that. So apparently we had a layer shift. This is the one line here that's looking out of context. I dialed accelerations down from 15 to 14k. It is on the y-axis, so this is the new bottleneck. So I've been running this on the first stage out of 3, and after 25 minutes of printing time it is still full battery, so lots of headroom there. Leakage wise, I don't know, I'm just gonna let it run. So we just had another layer shift. Next layer, watch out for the beep. So Julian did also program in the beep. Alright, so let's see what we got here. So first and foremost, This print took 56 minutes, and according to Slicer it should weigh 172 grams, including purge line, etc. And yeah, according to this kitchen scale, we're a bit off. We're 25 grams off. Let's make it 20. But let's address this first. This setup where I'm running the extruders right now is kind of janky. There is a single of these 5160 drivers, and I encountered this before. I cranked the amperage up to 3 amps, and still I could see those guys not turning when too high of accelerations are being asked. This is also on a 24 volt setup. The whole thing was planned very, very differently, but because of some bugs, and I have to contact Clipper developers about it, this was not running as intended. Don't want to be shaming on Clipper, this is running awesome as in general, but in this particular case, for this experiment, it is not. And I have to run it like this to get an even amount of pressure advance on both of these. So I'm guessing it is not because of melting capacities. This is way within our limit, but this is the high accelerations being asked when pressure advance is active is too much for this setup here. Well, yeah. And then we have to divide this into a few things. So when we want to review that hot end, and so we got to subtract everything that is printer mechanic related, and also this color combination here of black and bluish doesn't help judging what we're dealing with. I think in terms of raw extrusion, I'm pretty happy with the result. There is of course a lot to dial in, but this print here in particular was never designed to look good. This is a 0.6 millimeter nozzle, and I've been pushing 0.4 millimeter layer heights, just to be able to get somewhere close to melting capacities. So even with the printer running at high accelerations, 15K throughout most of the printing, using way more layer height than is being normal to such a print, we managed to average just above 40 cubic millimeters a second. Keep that in mind with every hot end data sheet you're gonna have a look at. If someone says 80 cubic millimeters is their flow capacity, that doesn't mean you can call that continuously. It may do it for short peaks. And if you think about it, this hot end would probably be able to do 200 peaks if there wasn't like skippage or something from the extruders. But I have proven in the max flow test that even 125 with the heaters being our bottleneck here is doable if we run continuous extrusions, and that's what I'm after with. Apart from that, let's have a look at our DMD surface. This one's black, this one's blue, and both of these are somewhere in the middle. You see, the filaments are entering the nozzle like this. And in this case, the blue can be seen from the outside. In this case, the black. And in this case, both of them are kind of like put down on top of each other. So you get this like gradient effect of 50-50. The thing where we can probably judge the hot end the best is top and bottom layers. And truth be told, they do look pretty crisp. Top and bottom was somewhere at 60 cubic millimeters a second continuous. Actually, have a look inside of here. There you can see the gradients that are being achievable, determined by the movement direction. The whole circular section down here is looking pretty damn fine. So I think we're gonna do what every good salesman would do. We're gonna print a vase, because these are easy. It is totally doable to achieve high flow rates. We're just gonna go with whatever 2 millimeter layer width on the 0.6 nozzle. We're gonna dial in 100 cubic millimeters of flow and just gonna send it. So the filament has been in here for like 20 minutes of me talking into the camera. Hotend has completely cooled down and I'm now heating it up again. Before this has been a problem here on the Heatbreak situation, let us see if I can unload it this time. Yes, I can do. Yeah, both of them. For interpreting tea leaves, this looks as I want to have it. So we're gonna load in another Fiberlogy high-speed PLA clear in burgundy color. And while we're conservatively bringing down our first layer of the vase, another thing I would like to mention is that the temperature of the whole cube thing here has been just at 210 degrees, so no crazy 270 or something to max out that flow. It is in a very, very reasonable range. Oh, I'm losing my silicone sock here. And speaking of temperatures, so we're gonna pump out a lot of material here. Peaking at 70 cubes for the first layer. Last time I did run into issues that the heat bed is getting increasingly warm here because of all the material deposited. Until now this doesn't seem to be the case. And yeah, I'm gonna bring you in a few moments. We're gonna extrude at 1.5 millimeters layer width and continuous 100 cubic millimeters of flow. Continuous 95 cubic millimeters. Heated bed is at 61 degrees. Look at those spools. And we've reached cruising speed. Again, stuck to the floor. This is at 225 degrees, just to have a bit more headroom and viscosity. Oh yeah, but I see leakage is bad. Oh my. I'm gonna have to pull that off constantly. Okay, I think I found the best setting for the Makita. In case you're really interested in that kind of solution, because I think it's quite powerful. Not with a battery setup, but with just a big leaf blower as CPAP solution. What I found with this here, the more you go on the throttle, the more back pressure the system builds, of course. And what ends up happening is that the exhausted air is going to get considerably warmer than on just standard settings. So I dialed it back down, and I think this is like the best effect on here. But of course, for again cooling down a vase print of that size, you're gonna be having some kind of a sheet cooling. Basically, you have a circle of something like that which is gonna be cooled, and not the whole print itself. So yeah, I'm just gonna let this roll. So of course I have looked into, is this Makita hackable? Basically set this up as a PWM signal and control it over the mainboard. It seems like it's not. Makita uses some proprietary signals there. The only thing you could do right off the box were like some mechanical thing that would actually squeeze the trigger, but yeah, not this time. So it did finish. I mean, have a look for yourself. So, what have we proven here? I think it's mainly two things. So first off, you can print continuously at really high flow rates. This print took 30 minutes and is expected to be 180 grams worth of filament. So let's say 350 or something per hour is totally doable. But cooling it down, especially on a rather small build plate like this, is a completely different story. Second thing to take away from here, I am not done with the development of this guy. So I've managed to get my SD card full, the battery is empty. It is again pretty late. I think it's time to wrap this video up. Haha, gotcha good. Just when you thought you could end your poop break on this probably 1.5 hour long video, you cannot, because now it gets interesting. When I was editing stuff, I felt the strong urge to answer some additional questions. So I reran the last Vase mode print, and now we got completely maxed out TMC driver up here on these guys. These are running 3 amps RMS. I also upped the currents on X and Y down there on the LDO Kraken motors. From 1 amp to 175, they're still, I guess, have plenty to go, but let's start somewhere. And then, and this is what I'm really excited about, I did a hot take on tightening the heat brakes. Got up to 250 degrees. These are holding up just fine, no leakage there. So I'm pretty excited about that. So I'll keep this running for a minute or two to see if anything overheats and stuff. Still, I'm pretty sure this setup is skipping material. There is no way all the peaks of the movement are actually performed by those extruders. So for the future, we have to upgrade that, make this independent stepper channels and see how we can apply pressure advance to both of them. But for now, I got one last thing in mind. Let's print a Benchy, and then, for goddamn sake, you can wipe, etc. Okay, I only got this one try, 0.4mm layer height. I pulled out some pressure advance value. It is at 0.12 right now to get rid of some of these peak values. Again, everything in terms of amps on the extruder driver. First layer is rather slow. The Benchy is scaled to 250%, should be 120 grams and just shy of 45 minutes, at least according to Slicer. Yes. Let me take that off the build plate, hit the bit of stringing we got here with a blowtorch and have a look at it. So if you ask me, for the little effort I've actually put into tuning this printer and Hotend, this is looking amazing. Sub 45 minutes print, slightest bit of stringing, but again no retraction test. No ideas on how the extruders perform, we'll put it on the scale now. 15K accelerations throughout the whole print. We'll have to check where our true limits are, but before I have to stiffen up the MK3 and my bench apparently. Then do another input shaper, yada yada. I'm so glad I took the time to do this test right at the end. I haven't checked it either. Slicer says 118 grams. Okay, so we're short 9 grams. But I guess upping the amperage on the driver as well as getting the PA value down seem to have helped. But I really can't see where this is missing 9 grams. So maybe it's just an error in the slicer's calculations. I think now is the time to wrap this video up. Conclusion time. So if you ask me, this whole setup here does show a huge amount of potential. I've only made a few successful prints up to now. There's no real dialing in of stuff, etc. But this could be a really fast machine once it's all said and done, because on the Creality we were pretty much limited by what the motion system could do. Now this is another story. And I thought the MK3 was a perfect machine because it is one of the most sold printers in history, but it has gotten a bit outdated. And I think many of you will have this somewhere in your shelf or your garage or whatsoever. And this might be a really worthwhile project of upgrading this. While it is slow to modern standards, you can make it 2-3 times faster than any of the out-of-the-shelf solutions from 2025. Just because you're able to put out a lot more plastics and the motion system is able to keep up. That being said, I'm really aware that we're not done with the development here. There is lots of stuff to figure out. We have to make it all reliable and bulletproof. So if you want to do the conversion of that system so you don't end up with all sorts of pain and trouble. I do have the workshop, the resources and sometimes the time to do all that stuff. And I got the support of my Patreons, we'll get to that in a minute. But of course, this is not the project for everyone. You will have to be really involved and don't fear tinkering around. So you really should know what you're getting into. But speaking of figuring stuff out. So I've been preparing the Github page in the background, and I'm gonna list now what you can find there. So first and foremost, you will find the 2x filament version of this Hotend. Since many people asked, I also uploaded this as step files, so you can see all the internals and yeah, pretty much change it up as you wanna have it. And of course also there is the edit step files of everything that you need to put it on this Prusa machine. It will run pretty much out of the box with the standard components that are out there. Prusa is really helpful in terms of getting firmware set up. I'm also going to put in the printer's firmware on there so you can figure out this on your own, or if you want to do the full conversion with really high accelerations and stuff, you've seen Julien's video about it. The files on the GitHub are with the latest generation of Heatbreaks installed, so the Chimera Heatbreak. As you've seen, when I fully tightened this guy, it did not leak at all. And this is what we want to have. This is a necessity. So I left the 4x filament version untouched because it was also working with me. But keep in mind, the higher you go with the pressure through the extruders, the more likely it is to encounter leakage. So there probably is a way to use the 4x filament with the Chimera Heatbreak, but you may encounter some things you have to do on your own if you don't want to buy new stuff. Probably you have to cut down the Chimera Heatbreak to make it the same form factor as the previous one. And then you have to take away approximately 1 millimeter on top of the Hotend itself, so it screws in all the way. If you want to source the parts for the Hotend and Coldend, you will again find step and STL files which you can upload to your SLM manufacturer. There is also a sophisticated drawing for uploading that to PCBWay, and I can give you some numbers beforehand. I don't earn a single cent with they producing it. The unmachined version, both hot and Coldend, will be around $70 for the package. And if you want to have all the threads, etc. and tolerances being held in by the manufacturer, then it's about $130. For the elephant in the room, the extruder setup, I do have some sophisticated plans for the future to eventually do it all with one motor and then have either gears or belts connect to, let's say, the easiest Amazon solution out there to make a 2 or 4x extruder really easy to build and really easy to hook up to the controller. This will not be for the mixing thing. We're gonna try that in an upcoming video as well. But I think the main use case for this kind of setup is to have equal flow rates to all of these melt channels. And we're gonna figure something out for that. But again, in a future episode. I want to keep going, dial this more in, find more stuff out, and then publish it with all of you guys. But this will be a thing of the future. I think the next video again will be around the Minuteman machine. I have set the plan to shave off 15 seconds from the latest print, which was sub 90 seconds. So there is again a huge leap to be made. And I think there are two main things I want to focus on. This is properly controlling the motors, so getting really deep into register profiles, etc., and dial everything to the last percent. And to be quite frank, we're gonna need that in order to run a sub 1 minute or 75 seconds for the next part. And then we're gonna focus heavily on getting the best slice out there, because every second counts, and I think slicing is the best option to go here. And then after I solve this at some point, we're gonna come back here. I think it's gonna be about the Prusa, but maybe we'll put it on a completely different machine. Maybe explore co-XY systems for once. I haven't fully made my mind up about that. So the last shot of this really long video will be adding a few more names to my Patreon list down there. Thank you so much for enabling me to do all this stuff basically in my free time here. Thank you. That being said, my name is Jan, and I build stuff so you don't have to. Bye.
Dauert. Monate dauert, 50 Minuten.
Overwhelming.